Well, just a little bit about the possibility of doing some solar design to finish off the semester. Let me get the ideas out there. We're not going to stress about it for right now. I'll try to be brief. Let's get going. So solar design would basically be we have something that we want to do and it involves energy, and we're going to try to capture solar energy in order to meet that need. So for your project, what I would love to do, and I realize that I've been slow in getting information out, is have you do a really short solar design for your short project. And it would be along the level, not of doing complicated calculations, but combining some things we've learned this year about available solar and how much solar we can capture. And then kind of like an engineering 124 level understanding of different devices out there. So try to clarify that. What I want to do is just share with you a rough outline of what I was thinking for possibly the design, but sure, just as what you might do if you were doing some solar design. So in anything we do in engineering, usually we start by calculating the energy requirements. So what I was thinking about doing, if we do end up having a project, more about that later, is give you a job, okay? And say, hey, there's a job that we want to do on a certain day, and you, junior engineer, are going to do a quick design for that. So here's an example. Let's say our day was May 1st, and our job was going to be cooling a gymnasium. Could we do that using solar energy? Absolutely. How would you do that? I want you to come up with a rough design. So the first step would be, if we were cooling a gymnasium, how much energy would that take? Well, more about that later, but I'm going to take us through these steps, 1, 2, 3, 4, 5, 6, 7, 8, for a simpler case, an option that would not be part of the project. So back to the whiteboard. No need to copy any of this down. I will post this Word document online. More just want you to follow what's going on and think about what's going on. And obviously this video is available to you. Okay, so let's just make the job that we're going to try to warm up 60 gallons of water for a family, hot water from a family. So we're going to try to get it from 60 to 120. Okay, no need to pull out any calculator. How much energy would that take? What would the energy input be? That would be your first step. So just a quick reminder, no need to do any calculations. I'm going to do MC delta T. Okay, the mass of 60 gallons is about 500 pounds. Specific heat of water is 1. If we raise it from 60 to 120, it turns out that that is going to give us a 30,000 BTU requirement. So we need 30,000 BTUs to go into the water. Okay, so how would we do this? Okay, well, what if I said the first thing I'm going to do, the system I'm going to try to design is going to have solar, get PV panel, make electrical flow, and that electrical flow go to a resistor in that tank. Well, hopefully you know enough by now that no, you wouldn't do that, that's going to be an expensive, bad design. But I can take a look at this and carry through. Okay, so going back to the list, it's going to be kind of awkward as we go back and forth, but I want you to have a feel for what this would be like. Okay, for right now, we got 30,000 BTUs. Okay, the next step 2 that I have right here, would be describe the energy, pardon me, goodness, sorry about that. Describe the machine device setup that will provide the required energy. I already did that. We're going to put an electric resistance heater in there, and that's going to warm the water. Okay, let's take a look at step 3. Give you guys a second. Y'all a second. Determine the energy input to the machine device setup. This input is to be captured solar. Okay, and it looks like I got a misspelling there. Sorry about that, electrical. Okay, so let's take a look at that again. Determine the energy input to the machine or device or setup. Okay, so I'm sorry, there's a little bit of glare here. Okay, but then what we're going to do is we're going to have this electric resistance heater in our water. That's the approach that's being suggested here. So I'll just call that as a resistor. Okay, would we need to put 30,000 BTUs into that resistor or more? Well, in this case, it's going to be more because the whole setup is not 100% efficient. So if I went with a pretty typical efficiency of 96%, I'm getting that I would need 31,250 BTUs to go in. So it's going to take a little bit more energy than actually gets into the water. All right, so we're working our way backwards to design. Over here is going to be the solar panel, etc. All right. This is the input to our machine or our device. Some of you might choose air conditioning, some of you might choose pumping, okay? This then is the output of our solar system. So what we want to do, I'll just go ahead and make a panel over here like this. So imagine that this is our panel. Is it going to be a solar thermal panel that heats up water, or is it going to be a panel that makes electricity? Well, for this particular job, this particular description, it's going to be electricity. So we want 31,250 BTUs of energy to go out like that. Okay, so we know the output, and now what we need to do is design this here. So let me go back to the list and see where we're at. You know, we've worked for, goodness, not very long, and we're already partway through this project. Okay, so number 4 says now we know the output of the solar system, and that's what I was pointing to up here. We have this output. Okay, so now what we're going to do is we're going to estimate how much incident solar radiation needs to hit this panel, because that's going to help us figure out how big that panel needs to be. Okay, so a lot of you might say, whoa, 31,250, but remember, collection by a panel isn't 100% efficient. So let's go back to the whiteboard and take a look at that. Okay, so if we're going to get 31,250 out of our panel, how much solar needs to hit there? Well, usually only 1% of the solar hitting our panel actually gets captured and delivered. And what are those percents like? Well, I'll ask you to do maybe just some quick research. I'm talking quick, I'm talking basic. We talked about some numbers before. Solar thermal, 30, 40, 50, 60, 70, depending on the situation. Sorry about that little bit of glare that's there. I'm going to try to share to see if I can avoid it a little bit more. Okay. PV, well, about 15% would be pretty typical. So about 15% of the energy hitting here is going to be there, and that allows us to go backwards and get what this energy is here. I'm just going to do a quick calculation on that. So 31,250. What number do I need so that I get 31,250? I'm going to round off on my calculator, okay? But I'm getting a pretty big number, okay? And I'm getting like 208,000 BTUs of energy actually need to hit that panel during the day, okay? Well, that's a lot. That means that this is going to be an expensive system to make, but that's good design. That's good design. We have a reasonable calculation there. All right, so we're making some good progress. Let's go ahead and do the next step. And the next step, again, shoot, I'm going to pause for a second and see if I can get rid of that glare. Sorry, guys. Sorry, y'all. All right, hopefully a little bit better. Okay, so let's see what step we are. I think I had 8 steps up there on the project. So okay, so we did number 5. We estimated the required incident solar radiation, 208,000 BTUs. Now, by the way, for the project, I'm going to ask you to do it for a day, not a rate. So we're going to try to position a panel so that 208,000 BTUs hit it over the course of the day. Well, how are you going to go about doing that? And that is number 6 on this list. You have the solar on a tilted spreadsheet that given you can, for any location on Earth and any day for that location, you can position a collector and figure out the BTUs per square foot that hit the collector over that day if I give you some basic solar data, which I will. So we recently went back to Excel and we did the collector tank model. We're going to finish that model off hopefully next week, but for the project, you would only need to the only spreadsheet you'd have to have down is the solar on a tilted surface. Okay, taking a little bit more detail, there I ask you to pick a good collector tilt. So you're going to fool around with that spreadsheet and change the tilt and see what works out well. And you're also going to change the azimuth. And then the spreadsheet, if you've done it correctly, will tell you how much you actually have hitting there, given you pick a certain area. And so that'll work out. Okay, so H actually is per square foot. If you combine it with area, you can get the required collector area. So step 6 and 7 essentially are to come up with the specifications of the collector. How many square feet is it? What direction does it face? How do you tilt it, etc. And then you are done with the work. You actually have a design of something useful. This is what people professionally get paid to do. Is as in one thing that people professionally get paid to do as engineers. One thing is to actually design some component and get into all the details, the stress analysis, the heat analysis, et cetera, to make a component work. Another is, okay, you have some job out there that needs to be done, heating, water, et cetera. Can you design a system that would do that? And this is like designing it at an engineering 124 level. I know some basic relationships on energy, and I can design a system to do it, particularly if I take some stuff that we know about solar. Okay, let's take a look at number 8, then, what the last task is on that. So number 8, I envision you go ahead and doing this work. You would be working in Excel. You might do a little research online on your possible system, and then you put together a brief report. Like I said, past semesters, I've really liked it when students have left the course with a report that they could take to a job interview. This, certainly you're welcome to put in extra effort to get to the point where you have that kind of detail, but it's late in the semester. This has been a very unusual semester. I think it's worth doing something basic to get a feel for the application of this. And if it's good, great. If not, it'll be good enough for a job interview, great. If not, I think it'll be good for this class. So you do a quick summary. And here I have written, this report analyzes the possibility of engineering a solar system to, and that would be whatever job that you end up selecting. And the system will require, and you might say it'll require this machine, a pump. It might require this much type of panel, a PV panel. It might require this much area, etc. Key for me is to do the system schematic. That is a big part of some engineering disciplines, where you take the mess of equipment and lay it out clearly so that a client can understand what it is that they would be purchasing if they asked you to engineer and then build the system. And then you would summarize your calculations and do a couple printouts from your Excel spreadsheet, and putting that together would provide a complete report. All right, let me talk about some alternatives. I don't want you to do water heating with PV because I don't want you to go to a job interview with that. But I'm just going to go through one other quick one really quickly, not numbers, just a surface level, and then I'll describe the rest. So let's talk about pumping water with a DC pump. So DC pumping is great. Not that I'm an expert on it, but it's really neat how the numbers work out. I would be keeping the job, if you were to do this, I would keep the job really simple. What if over the course of the day, we wanted to take some amount of water, a certain amount of gallons, and get it from here up to here? Okay, well, the first step would be to figure out how much energy is that going to take. And not to, I might need to remind you a little bit, but if you thought about it for a second, when you say, oh yeah, that's right, that's high school physics. To get how much energy does it take to raise water from one point to another? Well, you use the formula MGH. It's potential energy. You're increasing that water's potential energy, and that would tell you how much work it would take. Okay, how about doing it? Why is DC pumping kind of interesting if you're in solar? Well, those PV pumps are usually run by electricity, and so PV panels make direct current electricity. Most motors out there that we use here in the United States are AC, alternating current, but direct current is very, very efficient way to go with PV. So you would be thinking about getting some pump, and this is like, unfortunately, our washing machine pump died recently, so this is our combination washing pump, machine pump. Here's the inlet right here, so the water comes in here, and then the pump has an impeller here. Remember, a pump is like a salad shooter where it spins around and the water goes out by centrifugal force. And then it comes out here and then ends up flowing out there like that. So you take water that's draining from the tub, and then you pressurize it and it comes out here and you can shoot it out into your drain system. So over here, we got this pump right here like that. It's kind of a little bit hard to see. And of course, this is the motor. That motor could be run by AC, but there are motors out there that are DC, and you can get a small pump like this and run it with a PV panel. Very, very simple. Not a lot of hard wiring, et cetera, required. Kind of a neat do-it-yourself type project to get a small DC pump going. Okay, so take through the list, just going backwards a little bit without much detail. You would know the energy required. So if I were to symbolize this right here as my pump. Pardon me for just a second. I got that glare again, not good. Okay, I know how much energy that the pump needs to give to the water, okay, and I could figure out how much energy needs to go into a pump. I mean, something needs to give that pump so it can provide energy to the water, okay, and I could come up with this number if I could come up with an estimate of an efficiency of a pump. So just making up some numbers, okay, if this is, say, like 60 units of energy that goes to the water, okay, and the pump is 30% efficient, well, it's going to take a lot more energy input to the pump. So pumps are usually more efficiently than that, but I'm just going to do that really quickly. Okay, it turns out that I would need 200 units of energy then into the pump. And then I could work backwards and say, okay, where's that going to come from? That's going to come from my PV panel. Okay, and then I could work backwards and come up with the area of my PV panel, given the tilt and the azimuth I choose, et cetera. And I could put together a complete system saying, hey, here's this pump, here's this panel. This is, if our job requirement is to take, say, 1,000 gallons, and over the course of a certain day, like May 1st, use solar energy to get it up there, you could complete that design. All right, let me briefly talk about the alternatives that you have out there. So just take a look at that list that's on that Word document. You could do pumping water. So I would give you a certain number of gallons that need to be pumped over the course of the day. I'd give you the day, and then also I would give you some G data for that day, so you could go ahead and design the size of your posted panel. Okay, how about heating water? Well, the option there would be to use a heat pump, and you saw that on some homeworks that we did, and there was a brief problem with that on that quiz that we had recently. And so that you have the background to do. Cooling a building, that's often done by an air conditioner. An air conditioner has a COP just like a heat pump. I would give you some information and say, hey, here's what you need to quickly estimate how many BTUs need to be removed from the building. Then what's the machine that's going to do it? An air conditioner. You can go backwards from the COP of an air conditioner or calculate from the COP of an air conditioner what input would need to go into that air conditioner. And then you could, that input energy would come from a solar system, and you could calculate everything that way. Okay, the next option I have over there is actually a pretty interesting one. What if your project was to dry a crop? We talked about it very briefly, how you calculate the energy necessary to dry a crop. And that would be in BTUs. Basically, we think of a crop as having a certain water content. You've got to evaporate water requires thermal energy, and you could calculate that thermal energy very, very simply. And then the easiest solar application is to have an enclosure with glass over it, have the crop underneath glass. And you would say, what percent of the solar hitting that glass actually would get in? And you can just do a little bit of research up there and look at what a reasonable percent is and easily design that. Okay, and the last one is something that it'll be interesting to see over the next 10 years or so what happens. What if you were going to cool a building with a machine called an absorption chiller? Well, that would be very similar to this option right here, cooling a building with an air conditioner. What an absorption chiller does is it removes heat from a space, but the energy input to the machine, chiller, instead of being electricity, is in the form of heat. And solar systems are great in generating heat. So I would ask you maybe to pull out a couple simple descriptions that you can find online about what an absorption chiller is and design those systems. Okay, for sure, what I was hoping to do is give you a little bit of idea about how to go beyond just calculations we've done this semester, like what's the angle of incidence, or what is the diffuse direction radiation on a tilted surface, to say, hey, now I'm going to engineer a system. Those steps I gave you are pretty typical. Um, am I going to require you to complete a project? Well, I'm going to send you out an email, and I'd welcome some input. Here are my thoughts on it. What I've done in the past is made a project that required a bit of work before the end of the semester. That's tough at this point. What I would do is my thought would be to curtail the project so you can get through our test 2, which is going to be on Tuesday, and do a minimal amount of work. My intent would be then after test 2, which is on Tuesday, I'm thinking no more than 5 hours of work to complete this project and turn it in on the Friday of finals week. Electronic submission would be fine. In general, with the projects that I've had, I felt that students who dig in and don't just leave it to the last second and do a sloppy job end up meriting a reasonable grade, and I think that helps grade-wise. In any case, I do know this is an unusual semester, and so I would like some input from you. I think the thing that you, in the back of your mind is, can you make it through next week? We'll have 2 lectures. I'm not going to collect a homework assignment. I will make a homework number 9 based on the recent lectures, but it won't be large. Then get through next Tuesday when we have test 2, which will be on homework 6, 7, 8, and 9. Not Tuesday this coming week, but Tuesday of finals week. Take a deep breath, have maybe done a little bit of start on this stuff, and try to put something together and determine Friday. Enough said. I hope you guys have a great weekend. I'll be contacting you with more information soon. Take care.